Among the countless stars and galaxies, a few cosmic objects stand as titans, monsters of energy, mass, and magnetic fury. The universe is not a quiet place. Behind the peaceful sparkle of stars on a clear night lies a realm of unimaginable violence. Out there, in the vast darkness between worlds, exist objects so extreme they defy our understanding of physics. These are nature's ultimate creations, born from chaos, forged in fire, and wielding forces that could tear apart solar systems in seconds. Every night, light from these cosmic beasts reaches our planet. Some of it has traveled for billions of years, carrying secrets from the edge of time itself. What stories does this ancient light tell? What warnings does it bring? At the heart of nearly every galaxy lurks a monster that bends the fabric of space and time. Black holes, regions where gravity has won its final victory. Nothing escapes them, not even light itself. They are perfect traps, invisible hunters that grow by devouring everything around them. The largest ones, called supermassive black holes, weigh as much as billions of suns. They are the dark engines that power entire galaxies, yet we cannot see them directly. We only witness their terrible effects on everything nearby. Stars torn apart, matter heated to millions of degrees, space itself twisted into impossible shapes. Then there are the stars. Not the gentle sun that warms our planet, but the true giants. Blue supergiants burn with such ferocity that they live fast and die young, exhausting their fuel in mere millions of years. These stellar furnaces forge the heavy elements that make up our world, the iron in our blood, the calcium in our bones. When they die, they do not go quietly. They explode with the brightness of entire galaxies, seeding space with the building blocks of future worlds. From the ashes of these dying giants come pulsars, cosmic lighthouses spinning hundreds of times per second. Imagine a city-sized sphere of matter, so dense that a teaspoon of it would weigh as much as Mount Everest. These are neutron stars, the collapsed cores of massive suns, spinning so fast they create beams of radiation that sweep across space like searchlights. Each rotation is timed with such precision that they rival our best atomic clocks. They are the universe's metronomes, keeping perfect time across the cosmos. But even pulsars pale before their violent cousins, magnetars. These are neutron stars with magnetic fields 1,000 trillion times stronger than Earth's. Their magnetism is so intense it would dissolve you from 1,000 miles away, pulling apart the very atoms of your body. When magnetars quake, they release more energy in a fraction of a second than our sun produces in 100,000 years. These starquakes send waves of gamma radiation racing across the universe, briefly outshining everything around them. At the edge of the observable universe shine the quasars, the brightest sustained sources of light in existence. These ancient beacons are powered by supermassive black holes, feeding on enormous clouds of gas and dust. As matter spirals toward its doom, it heats up and glows with the light of trillions of stars. Quasars are so luminous they can be seen from the opposite end of the universe, 13 billion light-years away. They are glimpses into the cosmic past, showing us how violent the early universe truly was. And then there are the galaxies themselves, vast cities of stars, each containing hundreds of billions of suns, along with all their planets, moons, and mysteries. Some galaxies collide in slow-motion dances that last hundreds of millions of years, their gravitational embrace triggering the birth of new stars and feeding the giant black holes at their centers. The largest galaxies are true titans, containing over 1 trillion stars and spanning hundreds of thousands of light years across. Each of these cosmic giants represents a different face of power. Each pushes the laws of physics to their breaking point. They are the universe at its most extreme, its most beautiful, and its most terrifying. So we must ask, among all these titans, the all-consuming black holes, the spinning pulsars, the magnetic magnetars, the brilliant quasars, the dying supergiants, and the colliding galaxies, which reign supreme, what is the most powerful object the universe can create? The answer for the most powerful object begins 5.7 billion light years from Earth, in a place where gravity has become a god. Phoenix A sits at the center of the Phoenix Cluster, one of the most massive gatherings of galaxies ever discovered. This is not just another black hole. This is something that shouldn't exist. A gravitational anomaly so large that astronomers had to check their calculations multiple times before believing what they were seeing. 100 billion times the mass of our Sun. Let that number sink in. Our entire Milky Way galaxy, with its hundreds of billions of stars, weighs about 1 trillion solar masses. Phoenix A alone contains 1/10 of that mass, compressed into a region of absolute darkness. This single object outweighs many entire galaxies. The event horizon, the point of no return around a black hole, normally spans a few million miles for typical supermassive black holes. Phoenix A's event horizon stretches across 390 billion miles. To understand this scale, imagine traveling at the speed of light. It would take you over 36 hours just to circle this monster once. Our entire solar system, from the Sun to the orbit of Pluto, could fit inside Phoenix A's event horizon with room to spare. In fact, you could fit dozens of solar systems side by side within this sphere of darkness. But Phoenix A is not sleeping. It feeds. The black hole sits within a galaxy that blazes with unusual brightness. Every year, this galaxy gives birth to about 740 new stars, a rate almost unheard of in the modern universe. Most galaxies today, including our own, produce only a handful of stars annually. Something extraordinary is happening here, and Phoenix A is the conductor of this cosmic orchestra. Around the black hole swirls an accretion disk, a whirlpool of doomed matter spiraling toward oblivion. This is not a gentle process. As gas, dust, and torn apart stars fall inward, they accelerate to significant fractions of light speed. The material becomes so compressed and heated that it glows with the intensity of hundreds of billions of stars. Temperatures in the inner accretion disk reach hundreds of millions of degrees, hot enough to emit powerful X-rays that we detect from Earth despite the vast distance. The disk itself is structured like a cosmic hurricane. The inner regions spin faster than the outer regions, creating friction that generates tremendous heat. Matter doesn't simply fall straight into Phoenix A. It spirals inward gradually, losing energy through radiation. A single particle of gas might orbit the black hole millions of times before finally crossing the event horizon, its death spiral lasting thousands of years. As matter falls toward Phoenix AE, something remarkable happens. Not all of it is consumed. The intense magnetic fields threading through the accretion disk channel some of the infalling material into jets, beams of particles accelerated to nearly light speed and shot out from the black hole's poles. These jets extend for millions of light years into space, carving vast cavities in the surrounding gas clouds. The energy in these jets is almost incomprehensible, equivalent to the total energy output of trillions of stars. The Phoenix cluster itself tells the story of how this monster grew. Galaxy clusters are the largest gravitationally bound structures in the universe, containing hundreds or thousands of galaxies swimming in a sea of superheated gas. The Phoenix cluster is among the most massive ever found, and at its heart, Phoenix A has been feeding for billions of years. In the early universe, black holes grew rapidly through two methods: consuming gas and merging with other black holes. Phoenix A appears to have excelled at both. The cluster's enormous gravity pulls in rivers of gas from the surrounding cosmos. This gas flows toward the center, where Phoenix awaits. Unlike smaller black holes that might struggle to capture material efficiently, Phoenix A's immense gravity ensures a steady food supply. But gas alone cannot explain Phoenix A's enormous mass. This titan has likely consumed other black holes, perhaps thousands of them. When galaxies collide within the cluster, their central black holes eventually spiral toward each other and merge. Each merger adds mass to the victor. Phoenix A sits at the bottom of a gravitational well, so deep that over cosmic time, it has inevitably drawn in and absorbed countless smaller black holes from galaxies that ventured too close. The environment around Phoenix A is unlike anywhere else in the known universe. The galaxy hosting this monster shows signs of extreme activity. Vast bubbles of superheated gas, each larger than entire galaxies, have been blown into the surrounding cluster by the black hole's jets. These cavities in the hot gas glow in X-ray light, revealing the tremendous energy Phoenix A has pumped into its surroundings over millions of years. The cooling gas in the cluster core presents a puzzle. Normally, hot gas in galaxy clusters should cool and condense, forming new stars. But Phoenix A's jets reheat this gas, preventing it from cooling too much. It's a delicate balance. The black hole regulates star formation in not just its host galaxy, but in neighboring galaxies as well. Phoenix A is the thermostat for a region of space containing thousands of galaxies. Could Phoenix devour entire galaxies? The physics suggests yes, given enough time. Galaxies within the Phoenix cluster move through space at hundreds of miles per second, held in orbit by the cluster's combined gravity. Occasionally, these orbits bring galaxies close to the cluster's center, where Phoenix lurks. When a smaller galaxy passes too close, tidal forces, the same phenomenon that causes ocean tides on Earth, begin to tear it apart. The process starts subtly. Stars on the side of the galaxy closer to Phoenix feel stronger gravity than stars on the far side. This difference stretches the galaxy, pulling it into an elongated shape. As the galaxy draws nearer, the stretching intensifies. Eventually, stars begin to be pulled away, creating long streams of stellar material called tidal tails. But Phoenix A doesn't need to swallow stars directly to destroy a galaxy. Its gravitational influence disrupts the orbits of stars within the approaching galaxy, flinging some into intergalactic space while sending others plummeting toward the cluster's center. The galaxy's gas, the raw material for future star formation, is stripped away even more easily. Ram pressure from the cluster's hot gas combines with Phoenix A's gravity to leave the galaxy quenched, unable to form new stars. Over millions of years, the galaxy dissolves. Its stars disperse throughout the cluster, many eventually finding their way into Phoenix A's host galaxy. The gas becomes part of the cluster's hot atmosphere, some of it eventually cooling and falling toward Phoenix A to feed its accretion disk. In this way, Phoenix A grows not just by direct consumption, but by orchestrating the slow dissolution of entire stellar systems. Current observations show several smaller galaxies in the Phoenix cluster displaying signs of disruption. Long streams of stars stretch between galaxies, marking the paths of past encounters. These are the scars left by Phoenix A's gravitational influence, evidence of galaxies being slowly torn apart and absorbed. The most disturbing aspect of Phoenix A is that it continues to grow. Measurements of the gas flowing toward the cluster center suggest that Phoenix gains millions of solar masses each year. At this rate, it doubles its already staggering mass every few billion years. There appears to be no upper limit to how large it can become. The radiation from Phoenix A's accretion disk creates a zone of influence extending for millions of light years. Within this zone, the black hole's energy output affects everything, heating gas, triggering or suppressing star formation, and even influencing the chemical evolution of galaxies. Phoenix A doesn't just occupy space, it dominates and reshapes an entire region of the universe. Deep in the cluster's core, time itself behaves strangely near Phoenix A. The black hole's immense mass warps space-time so severely that time passes differently at various distances from the event horizon. If you could somehow survive near the event horizon, you would age more slowly than someone farther away. From your perspective, near the black hole, the outside universe would appear to speed up, stars living and dying in what seemed like moments. The X-ray telescopes that study Phoenix reveal constant variation in its brightness. The accretion disk flickers and flares as clumps of matter make their final plunge past the event horizon. Each flare represents the death of something, perhaps a star torn apart by tidal forces, or a massive cloud of gas finally succumbing to gravity. These variations tell us that Phoenix A is actively feeding right now, 5.7 billion years in the past, the time it took for its light to reach us. What Phoenix A represents is gravity's ultimate victory, a region where one of nature's fundamental forces has overwhelmed all others. No amount of pressure, no nuclear fusion, no electromagnetic repulsion can resist the pull beyond the event horizon. It is a one-way gate out of our universe, a place where the known laws of physics cease to function as we understand them. While Phoenix demonstrates gravity's silent dominance, 12 billion light-years away, burns something far more violent, a cosmic furnace that makes Phoenix look dim by comparison. S5 0014 plus 81 is not just bright. It is an abomination of light, a quasar that defies comprehension. Where Phoenix whispers with gravity, the quasar screams with radiation. This is luminosity taken to its absolute extreme, 300 trillion times brighter than our Sun. If the quasar were placed 280 astronomical units from Earth, about 7 times the distance to Pluto, it would appear as bright as our Sun in the sky. But it sits 12 billion light-years away, and we can still see it. This quasar belongs to the universe's violent youth. The light we see from the quasar left when the universe was less than 2 billion years old, a time when cosmic violence was the norm rather than the exception. Quasars are time machines, showing us an era when supermassive black holes grew with terrifying speed, feeding on vast reservoirs of gas that no longer exist in today's calmer universe. At the heart of the quasar lies a black hole of 40 billion solar masses, smaller than Phoenix AE, yet somehow generating far more energy. This paradox reveals a fundamental truth about black holes. Size alone doesn't determine power. What matters is how fast they feed. And the quasar feeds at nearly the maximum rate physics allows. The difference between a sleeping giant like Phoenix A and a raging quasar lies in their food supply. The quasar exists in a galaxy drowning in gas. Every second, matter equivalent to 4,000 suns pours into the black hole's accretion disk. This material doesn't fall quietly into darkness. It dies in the brightest way possible. As gas spirals toward the black hole, it forms a disk that spans light-years across. The inner edge of this disk reaches temperatures of billions of degrees, hotter than the center of any star. At these temperatures, matter doesn't just glow, it transforms. Atoms are stripped of their electrons. Protons and neutrons break apart. The disk becomes a soup of fundamental particles, radiating across the entire electromagnetic spectrum from radio waves to gamma rays. The efficiency of this process borders on the miraculous. When matter falls into the quasar, up to 40% of its mass converts directly into energy through friction and gravitational compression before crossing the event horizon. By comparison, nuclear fusion in stars converts less than 1% of mass into energy. The quasar is the universe's most efficient engine, extracting more energy from matter than any other known process. This energy doesn't radiate uniformly in all directions. The spinning accretion disk and the black hole's magnetic field create a natural focusing system. Like a lighthouse beam, much of the radiation emerges in 2 opposing jets perpendicular to the disk. These jets punch through the surrounding galaxy and extend into intergalactic space, carrying energy across millions of light-years. The host galaxy of the quasar, if we can even call it that, is completely overwhelmed by its central monster. The quasar's light drowns out the combined glow of hundreds of billions of stars. From our perspective on Earth, we see only the brilliant point of the quasar itself. The galaxy around it is invisible, lost in the glare, like a candle held in front of a searchlight. But we can infer the galaxy's presence through other means. The spectrum of the quasar's light reveals clouds of gas surrounding the quasar, some falling inward, some blown outward by radiation pressure. These clouds move at thousands of miles per second, their velocities traced by the Doppler shift of their spectral lines. The galaxy is there, but it exists in the shadow of its own center. The radiation from the quasar extends far beyond visible light. Radio telescopes detect powerful emissions from electrons spiraling in magnetic fields. X-ray observatories see the ultra-hot corona above the accretion disk. Gamma-ray detectors occasionally catch flares when the jets point directly at Earth. Each wavelength tells a different part of the story, revealing layers of violence stacked upon each other. The broad line region around the quasar spans several light years, filled with clouds of gas moving at up to 10,000 miles per second. These clouds glow from the intense ultraviolet radiation flooding out of the accretion disk. The atoms in these clouds are constantly being ionized and recombining, creating a forest of emission lines in the quasar's spectrum. By measuring these lines, astronomers can weigh the black hole and clock the speed of material orbiting it. Further out, the narrow line region extends for thousands of light years. Here, gas clouds move more slowly, but they still glow from the quasar's radiation. This region marks the boundary between the quasar's direct influence and the normal interstellar medium of the galaxy. Beyond this point, the radiation weakens enough that normal stars can exist, though normal is relative when living next to such a monster. The wind from the quasar is perhaps its most destructive feature. Radiation pressure from the quasar accelerates gas outward at speeds approaching 10% of light speed. This wind carries away more mass than the black hole consumes, clearing out the galaxy's gas reserves. It's a self-limiting process. Eventually, the quasar will exhaust its food supply and fade. But for now, the quasar burns at full power. The question of life becomes urgent when considering the quasar's output. Could anything survive in a galaxy hosting such a monster? Could life exist even in neighboring galaxies? The numbers are sobering. Within the quasar's host galaxy, the radiation field would be lethal to any form of life as we know it. The constant bombardment of high-energy photons would shatter DNA, break apart organic molecules, and strip away planetary atmospheres. Even on the night side of planets, the radiation reflecting off interstellar gas would deliver killing doses. Water, the foundation of life as we understand it, would be dissociated into hydrogen and oxygen by the intense ultraviolet light. These elements would then be ionized and blown away by the quasar wind. Rocky planets would see their surfaces baked and their atmospheres eroded. Gas giant planets would have their outer layers stripped away, leaving only their cores. But the danger extends beyond the host galaxy. The quasar's jets carry deadly radiation across intergalactic space. If Earth were in the path of one of these jets, even from 1,000,000 light-years away, the results would be catastrophic. The radiation would destroy our ozone layer within months. Ultraviolet light from the sun would then reach the surface unfiltered, causing mass extinctions. The upper atmosphere would be ionized, creating a cascade of chemical reactions that would further damage the protective layers around our planet. Even planets not directly in the jet's path would suffer. The broad radiation field from the quasar extends outward in a sphere, weakening with distance, but never truly disappearing. Calculations suggest that within a radius of several million light-years, the background radiation level would be high enough to significantly increase mutation rates and cancer incidence in any complex organisms. The most insidious effect might be on stellar nurseries. Regions of space where new stars and planets form require cold, dense molecular clouds. The radiation from the quasar heats and ionizes these clouds, preventing them from collapsing. In essence, the quasar sterilizes not just existing life, but prevents new life from ever beginning. It creates a dead zone around itself where planetary systems cannot form. The timescales involved make the situation even more dire. The quasar has been burning at this intensity for millions of years and could continue for millions more. Any civilization developing in a nearby galaxy would face constant bombardment throughout its entire evolutionary history. The radiation would be a permanent feature of their sky, a deadly rain that never stops. Consider what this means for the distribution of life in the universe. Around every quasar, there exists a zone of death, a region where life cannot arise or survive. During the quasar era of the early universe, when objects like the quasar were common, vast regions of space would have been permanently sterilized. Life might have been confined to quiet backwaters, far from the centers of galaxies where quasars burned. The chemical enrichment from the quasar adds another layer to this story. The quasar wind carries heavy elements forged in the accretion disk out into intergalactic space. These elements, carbon, oxygen, iron, are essential for life, yet they're being dispersed by the very process that makes the region uninhabitable. It's a cosmic irony. The quasar spreads the ingredients for life, while simultaneously making life impossible. From the ancient violence of quasars, we return closer to home, to our own galaxy, where a different kind of monster exists, not one of gravity or blinding radiation, but of pure, overwhelming size. Scuti defies our sense of scale. This star is so large that light itself takes hours to cross from one side to the other. Located 9,500 light-years from Earth in the constellation Scutum, Scuti is a red hypergiant, a star that has swollen to dimensions that shouldn't be possible. Its radius extends 1,700 times farther than our Sun's. Numbers fail to convey what this means. If Scuti replaced our Sun, its surface would extend beyond the orbit of Jupiter. Mercury, Venus, Earth, Mars, and Jupiter would all orbit inside the star itself. Saturn would barely escape, skimming just above the star's bloated photosphere. The inner solar system wouldn't just be vaporized, it would cease to exist as separate entities, becoming part of the star's outer layers. But Scuti's surface is nothing like our Sun's. Where our Sun has a relatively sharp boundary between its interior and the vacuum of space, Scuti fades gradually. Its outer layers are so tenuous they're closer to a hot vacuum than what we would consider stellar material. The density at UY Scuti's visible surface is less than the air at Earth's surface. You could fly a spacecraft through the star's outer atmosphere, though it would be instantly vaporized by the temperature. This ethereal surface hides internal violence on a scale that dwarfs anything in our solar system. Inside UY Scuti, convection cells larger than Earth's orbit rise and fall. These are columns of superheated gas, each carrying more energy than our Sun produces in a year. They rise from the star's depths at speeds of hundreds of miles per second, cool slightly at the surface, then plunge back down to be reheated. Each convection cell is a world unto itself. The rising columns glow white hot, while the descending material is darker and cooler. From Earth, we see these patterns as variations in the star's brightness. UY Scuti pulsates irregularly, its light output varying as massive convection cells break through the surface and subside. These pulsations occur on timescales of months to years, each one involving the movement of more mass than exists in our entire solar system. The temperature at UY Scuti surface is relatively cool by stellar standards, about 3,300 degrees Celsius compared to our Sun's 5,500 degrees. This low temperature is why the star appears red. But this coolness is deceptive. The total energy output from UY Scuti is 340,000 times greater than our Sun's. Every second, UY Scuti radiates enough energy to power a human civilization for billions of years. This tremendous luminosity comes at a price. UY Scuti, burning through its nuclear fuel at a catastrophic rate. While our Sun will shine steadily for 10 billion years, UY Scuti's life is measured in mere millions. The star is already near death, though near, in cosmic terms, still means hundreds of thousands of years. Inside UY Scuti's core, the situation is extreme beyond imagination. The temperature exceeds 300 million degrees, hot enough to fuse not just hydrogen into helium, but helium into carbon, carbon into oxygen, and oxygen into silicon. The star has become a factory for heavy elements, its core resembling an onion with different layers fusing different elements simultaneously. The radiation pressure from these fusion reactions is what holds UY Scuti up against its own gravity. But it's a precarious balance. The star constantly teeters on the edge of collapse. Small changes in the fusion rate cause the entire star to expand or contract by distances greater than Earth's orbit. These oscillations send shockwaves through the star's interior, each one powerful enough to destroy planets. UY Scuti's stellar wind is a hurricane that never stops. The star loses mass at a rate of about 1 Earth mass every year, blown away by its own radiation. This wind extends for light years around the star, creating a bubble of hot gas in interstellar space. Any planets that might have once orbited UY Scuti have long since been stripped of their atmospheres and eroded away by this constant gale. The composition of UY Scuti tells the story of its evolution. Spectroscopic observations reveal an atmosphere enriched with heavy elements, carbon, oxygen, and nitrogen that have been dredged up from the star's interior by convection. These elements form complex molecules in the star's cool outer layers: titanium oxide, water vapor, Even simple organic compounds. UY Scuti is a chemical factory operating on a stellar scale. The star's magnetic field adds another layer of complexity. While much weaker than the fields around neutron stars or magnetars, UY Scuti magnetic field is still powerful enough to channel the stellar wind and create hotspots on the surface. These magnetic structures are constantly being created and destroyed by the roiling convection, leading to unpredictable variations in the star's spectrum and brightness. Surrounding you, UY Scuti is a vast shell of gas and dust, material the star has shed over thousands of years. This circumstellar envelope extends for several light years and glows with infrared light. The dust grains in this envelope are factories themselves, sites where complex molecules form from the elements expelled by the star. Some of these molecules will eventually be incorporated into new planets around future stars. The fate awaiting you, UY Scuti, depends on its exact mass, which remains uncertain due to the difficulty of weighing such a distant, variable star. If UY Scuti is less than 20 times the Sun's mass, which seems likely given its current state, it will end its life as a supernova. But this won't be an ordinary stellar explosion. When fusion finally stops in UY Scuti's core, nothing will remain to hold the star up against gravity. The core will collapse in less than a second, reaching densities where protons and electrons merge into neutrons. This collapse will release a flood of neutrinos, ghostly particles that rarely interact with matter but carry away enormous energy. The neutrino burst from UY Scuti. Death will briefly outshine the entire visible universe in neutrino light. The collapsing core will rebound, sending a shock wave outward through the star. This shock wave will take hours to reach UY Scuti's bloated surface, but when it does, the results will be spectacular. The star's outer layers will be ejected at speeds of thousands of miles per second. For weeks, the supernova will shine with the light of billions of suns visible from neighboring galaxies. But there's another possibility. If UY Scuti is more massive than current estimates suggest, it could die in an even more violent event, a hypernova. In this scenario, the collapsing core forms a black hole surrounded by an accretion disk of infalling stellar material. Jets of matter, accelerating to near light speed, would punch through the star's poles, creating gamma ray bursts that could be detected from across the universe. The energy released in a hypernova exceeds that of ordinary supernovas by factors of hundreds. The explosion would completely unbind UY Scuti, leaving no remnant except a black hole. The ejected material would be accelerated to significant fractions of light speed, creating a supernova remnant that would glow for thousands of years. Either way, UY Scuti's death will enrich the surrounding space with heavy elements. Iron forged in the star's final moments, gold and uranium created in the explosion itself. These elements will drift through space for millions of years before being incorporated into new stars and planets. Every atom of these elements on Earth came from a dying star. The shockwave from UY Scuti's explosion will compress nearby gas clouds, triggering the formation of new stars. In this way, the death of hypergiants like UY Scuti drives the continued evolution of galaxies. They are stellar phoenixes, their deaths giving birth to new generations of stars. Currently, UY Scuti shows signs of increasing instability. Observations over the past century reveal growing irregularity in its pulsations. The star occasionally experiences massive eruptions, ejecting shells of gas at high velocity. These events might be precursors to the final collapse, though predicting exactly when a star will explode remains beyond our capability. The surface gravity on UY Scuti is about 100,000 times weaker than on Earth, despite the star's enormous mass. This is due to the vast distance between the surface and the center of mass. If you could somehow stand on UY Scuti's surface, you would weigh less than a gram. But you would also be immediately vaporized and blown away by the stellar wind. The low surface gravity means UY Scuti barely holds onto its outer layers. The star exists in a state of near dissolution, its outer envelope so loosely bound that relatively small disturbances can eject massive amounts of material. Solar flares that would be minor events on our Sun can lift entire Earth masses of gas from UY Scuti's surface. Deep inside UY Scuti, time runs differently. The intense gravity near the core causes gravitational time dilation. Time passes more slowly there than at the surface. Over the star's lifetime, this effect accumulates. The core has aged days less than the surface, though both have existed for the same number of years by external clocks. The convection patterns inside UY Scuti are chaotic in the mathematical sense. Small changes in conditions can lead to vastly different outcomes. A slightly hotter bubble of gas rising from the core can trigger a cascade of effects that alter the star's brightness months later. This sensitivity to initial conditions makes UY Scuti's behavior fundamentally unpredictable beyond short timescales. Observations in different wavelengths reveal different aspects of UY Scuti. In visible light, we see the star's photosphere. In infrared, we detect the warm dust in its circumstellar envelope. Radio observations reveal molecular clouds around the star, while ultraviolet light shows hotspots where magnetic fields channel energy. Each wavelength provides a piece of the puzzle, but the complete picture remains elusive. The stellar wind from UY Scuti creates a bow shock as the star moves through space. Like a boat moving through water, the star pushes interstellar gas ahead of it, creating a compressed region that glows in infrared light. Behind the star trails a wake of disturbed gas that will take thousands of years to settle back to equilibrium. When stars like UY Scuti finally collapse, they sometimes leave behind something that represents the opposite extreme, not vast and tenuous, but impossibly small and dense. In the constellation Sagittarius, 18,000 light-years away, spins the fastest rotating object ever discovered, PSR J174 82446 AD. This pulsar completes 716 full rotations every second. To grasp this speed, consider that its equator moves at nearly 1/4 the speed of light. A point on its surface travels 30,000 miles in the time it takes you to blink. This object, no larger than Manhattan, spins faster than the blades of a jet engine, faster than any mechanical device humans have created, approaching the theoretical limit of how fast matter can rotate without tearing itself apart. The object itself is a neutron star, the collapsed core of a massive star that exploded long ago. When a star 8 to 20 times our Sun's mass runs out of nuclear fuel, its core collapses so violently that protons and electrons are crushed together into neutrons. What remains is a sphere of nuclear matter 12 miles across but containing more mass than our Sun. The density defies comprehension. A sugar cube-sized piece would weigh 100 million tons on Earth. But density alone doesn't explain the rotation. When the original star collapsed, it carried its rotation with it. Like an ice skater pulling in their arms to spin faster, the shrinking stellar core accelerated dramatically. A star that once rotated every few days now spins hundreds of times per second. The conservation of angular momentum, a basic law of physics, creates this cosmic dynamo. The surface gravity on this pulsar exceeds Earth's by 200 billion times. If you dropped an object from 1 meter above the surface, it would strike at 4.3 million miles per hour. The escape velocity, the speed needed to break free from the surface, approaches half the speed of light. Mountains on this neutron star, if they exist, can be no taller than a few millimeters before gravity crushes them flat. The magnetic field threading through this pulsar carries a strength a trillion times more powerful than Earth's. This field, spinning with the star, creates an electric generator of staggering proportions. The rotating magnetic field accelerates charged particles to near light speed, creating beams of radiation that sweep through space like lighthouse beams. Each rotation sends a pulse of radio waves, X-rays, and gamma rays across the cosmos. These beams don't emerge from the entire star, but from hot spots near the magnetic poles. As the star spins and the beams sweep past Earth, we detect regular pulses, hence the name pulsar. The timing of these pulses is so precise that they rival atomic clocks. Over years of observation, the pulse arrival times can be predicted to nanosecond accuracy. The interior of this neutron star remains one of the universe's great mysteries. The outer layer is likely solid, a crystalline lattice of atomic nuclei arranged in a grid, swimming in a sea of superfluid neutrons. This crust experiences starquakes, sudden rearrangements that release more energy than our Sun produces in years. These quakes can alter the star's rotation rate, causing glitches in the otherwise perfect timing of the pulses. Deeper inside, matter exists in states impossible to create on Earth. The pressure exceeds anything in terrestrial laboratories by factors of billions. Neutrons might break down into their constituent quarks, forming exotic matter. There might be hyperons, particles containing strange quarks. The core might even contain a soup of free quarks, unbound from their usual groupings. Each possibility would affect the star's mass and rotation in measurable ways. The centrifugal force at this pulsar's equator is extraordinary. Matter there experiences an outward pull that nearly equals the inward pull of gravity. The star is oblate, flattened at the poles like Earth, but to a much greater degree. If it spun just 50% faster, centrifugal force would overcome gravity, and the star would fly apart, spraying nuclear matter into space at relativistic speeds. This particular pulsar didn't achieve its incredible rotation rate alone. It's a recycled or millisecond pulsar, spun up by matter stolen from a companion star. For millions of years, gas from a neighboring star spiraled onto the neutron star's surface, each infalling particle adding its angular momentum to the spin. This process, called accretion-powered spin-up, transformed an old slow pulsar into the speed demon we observe today. The companion star that donated this matter has been reduced to a burned-out cinder, a brown dwarf orbiting the pulsar every 26 hours. The pulsar's radiation and particle wind continue to erode this companion, slowly vaporizing it. In a few billion years, nothing will remain but the pulsar spinning alone in space, having consumed its partner entirely. The energy output from this pulsar's rotation is enormous. As it spins, it loses rotational energy through magnetic braking. The magnetic field carries away energy, gradually slowing the spin. This energy emerges as radiation and a wind of charged particles moving at near light speed. The total power output exceeds our sun's by factors of thousands, all from an object smaller than a city. The precision of pulsar timing opens remarkable possibilities. Networks of pulsars across the sky could serve as a galactic positioning system. By measuring the arrival times of pulses from multiple pulsars, a spacecraft could determine its position anywhere in the galaxy to within a few miles. This natural navigation system requires no satellites, no ground stations, just the ability to detect and time pulsar signals. Pulsars also act as laboratories for testing fundamental physics. The regular pulses pass through the warped space-time around massive objects, allowing us to test Einstein's general relativity in regimes impossible to access on Earth. Binary pulsars, where two neutron stars orbit each other, have confirmed the existence of gravitational waves decades before they were directly detected. The fastest pulsars push matter to its limits. The nuclear material at the surface must withstand stresses that would instantly vaporize any earthly substance. The magnetic field lines are so dense they affect the vacuum of space itself, creating regions where matter and antimatter spontaneously appear from nothing, only to annihilate microseconds later. The temperature at this pulsar's surface reaches millions of degrees, hot enough that the thermal radiation peaks in X-rays rather than visible light. But the temperature isn't uniform. The magnetic poles, where particles crash into the surface, glow even hotter. These hotspots, no larger than city blocks, outshine entire normal stars in X-ray light. Surrounding the pulsar is a magnetosphere, a region dominated by the magnetic field rather than gravity. This magnetosphere extends for thousands of miles, filled with electrons and positrons moving at relativistic speeds. These particles emit synchrotron radiation as they spiral along magnetic field lines, creating a nebula of high-energy light around the pulsar. The particle wind from this pulsar creates a bubble in interstellar space, pushing back the surrounding gas and dust. Where this wind meets the interstellar medium, a shock front forms, heating gas to millions of degrees. This pulsar wind nebula glows across the electromagnetic spectrum, a signature of the neutron star's power affecting space for light years around. Time itself behaves strangely near this pulsar. The intense gravity causes significant time dilation. Clocks on the surface run 30% slower than clocks far away. Combined with the rapid rotation, this creates complex relativistic effects. Different parts of the star age at different rates. The equator, moving fastest, ages slightly slower than the poles due to velocity-based time dilation. The pulsar's rotation provides a historical record written in millisecond precision. By carefully measuring how the rotation rate changes over time, astronomers can detect the gravitational influence of passing stars, the effect of the galaxy's gravitational field, and even the recoil from asymmetric particle emission. The pulsar is both clock and logbook, recording interactions spanning millions of years. The matter falling onto this neutron star from its companion doesn't accumulate smoothly. It builds up in a layer until the pressure and temperature trigger thermonuclear fusion. The entire surface can ignite in seconds, a runaway fusion reaction that briefly outshines the steady emission by factors of thousands. These X-ray bursts last seconds to minutes, each one releasing more energy than our sun produces in a week. Between these dramatic bursts, the accreted matter undergoes strange transformations. The immense pressure can create exotic forms of matter, crystallized carbon, solid oxygen, metallic hydrogen. These materials, impossibly compressed, have properties unlike anything on Earth. They might be superconducting, carrying electrical current with no resistance. They might be superfluid, flowing without friction. The magnetic field lines emerging from this pulsar extend far into space, but they're not static. They twist and reconnect, releasing bursts of energy. These magnetic reconnection events accelerate particles to energies higher than any human particle accelerator can achieve. The pulsar is a natural laboratory for high-energy physics, creating conditions that existed only in the first microseconds after the Big Bang. Navigation using pulsars wouldn't be limited to our galaxy. Each pulsar has a unique signature, its rotation period, how that period changes over time, and the shape of its pulses. A catalog of pulsar signatures would work anywhere in the universe. A spacecraft arriving in a distant galaxy could orient itself by identifying known pulsars, determining both its location and the time elapsed since leaving Earth. The discovery of pulsars this fast required special techniques. Traditional radio telescopes couldn't sample fast enough to resolve individual pulses. New digital systems had to be developed, capable of recording data millions of times per second. Even then, the signal processing required to extract the pulsar signal from the noise pushed computers to their limits. While the previous pulsar demonstrates nature's limits of rotation, 20,000 light-years away in the constellation Sagittarius lurks something that pushes a different boundary entirely. SGR 1800-620, a magnetar whose magnetic field represents the strongest force ever measured in the universe. This magnetar's magnetic field strength reaches 100 billion Tesla. For comparison, Earth's magnetic field measures 10 to the power -5 Tesla. The strongest sustained magnetic fields humans can create reach about 45 Tesla. This magnetar's field exceeds our best efforts by billions of times, creating an environment where the normal rules of matter and energy break down completely. On December 27, 2004, this magnetar reminded the universe of its power. A massive reorganization of its magnetic field A starquake in its solid crust released more energy in 1/10 of a second than our sun produces in 150,000 years. The burst of gamma rays and X-rays that erupted from the magnetar was so intense that, despite originating 20,000 light-years away, it overwhelmed satellite detectors designed to study much weaker sources. When this flash of radiation reached Earth, it had traveled for 20,000 years through the vacuum of space, weakening with distance according to the inverse square law. Yet when it arrived, it was still powerful enough to ionize Earth's upper atmosphere, creating effects usually seen only during major solar storms. Radio communications were disrupted. The ionosphere, the charged layer of our atmosphere that reflects radio waves, was physically compressed by the radiation pressure. The gamma-ray flash was brighter than the full moon in gamma-ray light, making this magnetar briefly the brightest object in Earth's sky outside our solar system, though invisible to human eyes. Spacecraft throughout the solar system detected the burst. Even satellites facing away from the source registered the flash as gamma rays bounced off the moon and planets. The energy release didn't stop with that initial flash. For minutes afterward, the magnetar rang like a bell, its solid crust vibrating from the starquake. These vibrations modulated the X-ray emission, creating a pattern that revealed the frequencies at which a neutron star naturally oscillates. Each oscillation mode corresponds to different ways the star can vibrate. Some compress the entire star, others create traveling waves around the equator, still others twist the star's shape. To understand what triggers such events, we must examine the magnetar structure. The magnetic field doesn't simply surround the star. It threads through it, emerging from the interior, looping through the magnetosphere, and diving back into the crust elsewhere. These field lines carry enormous stress. Where they emerge from or enter the surface, they exert pressure that can crack the stellar crust like tectonic plates on Earth. The crust of this magnetar is perhaps the strongest material in the universe, a crystalline lattice of atomic nuclei compressed to nuclear density. Yet even this extraordinarily rigid material cannot withstand the magnetic stresses indefinitely. The field slowly evolves, twisting and stretching the crust until it suddenly fractures. The energy released in these fractures powers the observed flares. Inside the magnetar, the magnetic field affects matter in ways impossible anywhere else. At field strengths above 10 billion Tesla, atoms cease to exist in their normal form. The electron clouds that usually surround atomic nuclei are compressed into thin cylinders aligned with the magnetic field. Atoms become needle-shaped, thousands of times longer than they are wide. Chemistry as we know it cannot exist. The vacuum itself behaves differently in these extreme fields. Quantum mechanics predicts that empty space constantly creates virtual particle pairs, an electron and positron that appear and immediately annihilate. Near this magnetar, the magnetic field can prevent these pairs from recombining, turning virtual particles into real ones. The vacuum literally boils with particle creation. Light passing through this magnetic field doesn't travel normally. The field causes vacuum birefringence. Photons split into two polarization modes that travel at slightly different speeds. A pulse of light becomes smeared out, its polarization rotating as it propagates. This effect, predicted by quantum electrodynamics but never observed in laboratories, occurs naturally around magnetars. The surface temperature of this magnetar reaches 10 million degrees, hot enough that the thermal radiation peaks in X-rays. But the temperature isn't distributed evenly. The magnetic field channels heat flow, creating hotspots where field lines concentrate and cooler regions where the field is weaker. The surface resembles a patchwork of different temperatures, each patch glowing with different intensity. The magnetar's rotation, once every 7.5 seconds, is gradually slowing. The magnetic field acts as a brake, carrying away rotational energy. But this slowing isn't smooth. The magnetar experiences glitches, sudden speedups when the crust cracks and the star's shape changes slightly. After each glitch, the rotation resumes its gradual decline, but at a slightly different rate. The connection between magnetars and fast radio bursts has become increasingly clear. These mysterious flashes of radio waves, lasting milliseconds but releasing enormous energy, were first discovered in year 2007. For years, their origin remained unknown. Then, in April 2020, a magnetar in our own galaxy produced a fast radio burst, confirming what many had suspected. At least some of these enigmatic signals come from magnetar flares. The mechanism likely involves the magnetosphere, the region around the magnetar dominated by its magnetic field. When magnetic field lines suddenly reconnect, they can launch clouds of plasma at relativistic speeds. As these plasma clouds plow through the surrounding magnetosphere, they generate coherent radio emission through a process similar to how pulsars create radio waves, but far more powerful. This magnetar sits in a unique environment. The 2004's giant flare excavated a cavity in the surrounding interstellar medium, creating a bubble of hot, low-density gas. Subsequent smaller flares maintain this cavity, keeping it clear of the dust and gas that fills most of interstellar space. The magnetar has created its own void, a region where its influence dominates over the normal interstellar environment. The X-ray spectrum from this magnetar reveals absorption lines that shouldn't exist. These lines, called proton cyclotron features, occur when protons in the magnetosphere absorb X-rays at specific energies related to the magnetic field strength. The detection of these features provided direct measurement of the field strength, confirming the incredible values predicted by theory. Surrounding the magnetar is a wind of particles, electrons, positrons, and ions, accelerated to nearly the speed of light by the rotating magnetic field. This wind carries away energy and angular momentum, contributing to the magnetar's spin down. Where the wind meets the interstellar medium, it creates a pulsar wind nebula, though fainter than those around ordinary pulsars due to the magnetar's slower rotation. The magnetic field configuration around this magnetar is far from simple. Instead of a neat dipole like Earth's field, the magnetar's field is multipolar, a complex arrangement of magnetic poles and twisted field lines. This complexity arises from the field's origin deep in the neutron star's interior, where convection and differential rotation create a magnetic dynamo. The lifetime of a magnetar's extreme field is limited. The field gradually decays through ohmic dissipation. Electrical resistance in the star's crust slowly converts magnetic energy into heat. This decay takes about 10,000 years, making magnetars cosmic mayflies. For every active magnetar we observe, hundreds of dead ones must exist, their fields decayed to ordinary pulsar levels. During its active lifetime, this magnetar will experience hundreds of smaller flares between giant events. These smaller outbursts, releasing only as much energy as the sun produces in years or decades, occur monthly or even weekly. Each one provides data about the magnetic field configuration and how it evolves over time. The gravitational field around this magnetar warps space-time measurably. Light passing close to the star follows curved paths, an effect called gravitational lensing. This bending is strong enough that we can see parts of the far side of the star. Its gravity bends light around itself. The combination of gravitational lensing and rapid rotation creates complex patterns in the observed X-ray emission. The 2004 flare from this magnetar may have had effects beyond Earth. Any planets within a few light years would have experienced severe atmospheric stripping. The radiation would have broken apart molecules in their upper atmospheres, allowing the constituent atoms to escape to space. Over time, repeated flares could completely erode a planet's atmosphere, leaving it a barren rock. The study of this magnetar requires special techniques. Normal X-ray detectors saturate when observing such bright sources. Scientists must use indirect methods, like watching X-rays bounce off dust clouds near the magnetar to study its emission without overwhelming their instruments. It's like studying the sun by looking at its reflection rather than directly at it. The internal structure of this magnetar remains partly mysterious. The core might contain free quarks, hyperons, or even more exotic particles. The magnetic field affects these particles differently than normal matter, potentially creating regions where different phases of matter coexist. The star might have layers, like an onion, each composed of different exotic materials. Theoretical models suggest this magnetar formed from a star at least 30 times our sun's mass. When this progenitor star exploded as a supernova, something unusual happened. Perhaps the core was rotating exceptionally fast, or perhaps it had an unusually strong magnetic field to begin with. The exact conditions needed to create a magnetar rather than an ordinary pulsar remain debated. The magnetic pressure inside this magnetar is comparable to the matter pressure. This means the magnetic field significantly affects the star's structure, making it larger than a non-magnetic neutron star of the same mass. The field also affects the star's oscillation modes, creating unique vibration patterns that serve as fingerprints of the internal field configuration. Energy storage in this magnetar's magnetic field exceeds 1,047 ergs, more than our sun will produce in its entire lifetime. This energy slowly leaks out through flares and particle winds. By the time the field decays completely, the magnetar will have radiated away energy equivalent to a significant fraction of its rest mass energy.